Okay, so good morning. And so last lecture, we were introduced to the idea of functionals. So these are functionals are things which take input as a function and give out a number. Okay, so it just generalizes our idea of it. So it's a function of a function, which is called functional. And today we will, we wrote Taylor series to first order for functional, and we defined a kind of derivative. So this thing goes by the terminology for functional calculus, and we saw that we needed to extremize functionals, at least in the example that we considered. So for instance, we wanted to solve the Brachistochrone problem, which was to find this function z of x, which takes the least time. So there was this time functional that we wrote, and we did some algebra, and we got this formula. And so the first step in finding the least time solution is to take this functional derivative and set it equal to 0. Okay, so today we will consider more examples. We did two. Yes, can I? Is there a question? Okay. So we'll consider more examples and also compute the functional derivative so that we get some handle. Okay, so we're going to do examples. So the first example is of a functional. So first thing is, before we do the examples, let me fix on. Okay, so we will consider functions on the interval zero to some positive number 0t. Okay, so q of t. So t will belong to this, so q of t, and what we will do is we are given q of t are all our functions that map the interval to r. Okay, and with further q of 0 and the endpoints, right? Q of t are fixed. Okay, so we are so the picture is that let's say, let me draw. This is 0, and let's say this is t, and let's draw one more line. So let's say it takes some value. This is q of 0 and this is q of t, and we are looking at functions. Let's draw one example. Some function like this. Okay, so this is an example. So these are the class of functions we are going to look at, and so we want to look at examples. The first example is let t naught any time which is in the interval 0 to t, doesn't include the endpoints. Okay, and then I'll define the function and consider the functional. Okay, so let us see what this functional does. This functional, what it does is it takes, you give it a curve q, if you give it any function q, it gives you the value of q at that time t naught. Is this clear, this functional, what this functional is? Anybody? Is this okay? Or this is a functional, right? Because q
Sir,
of t.
please tell that once more.
My question is this a functional? Do you agree it's a functional?
Yes, sir.
That's all. Okay, so now we want to do the functional derivative of this. So we remember our thing, what we did was we would take I at t naught and q plus delta q and minus okay, so these are two different functions, and so this, if you use the right hand side, it will just tell you it is q plus at t naught plus delta q at t naught, okay, times okay, so we can cancel things, so let's cancel it. So this cancels with this. Okay, so we get delta t naught, which I will just write in a slightly different way. Dirac delta function, delta. Okay, so let me also erase this. And this. Okay, so this is to identify the functional derivative, right? So if you remember last time, we recall if you have any functional f of q, if you remember, we wrote this as follows. We did the Taylor. Okay, so that's why I had to write it this way. Okay, so now we can see that this quantity is the same, is this, it's analog of that. Is this clear? So what we get is delta I at t naught divided by delta at q of t is equal to, okay, but what is I of t naught? It's also delta of q at t naught divided by, this is delta of q of t, the functional derivative, this is equal to delta of t. Okay, so any questions with regard to this computation?
Hello, sir. How did this ratio of delta of qt and divided by delta of q of t naught is defined as delta of t minus t naught?
This is our functional, right? I'm showing you this functional, right? This is your functional. I of t naught of q. That is q of t naught. So
No, I mean this thing, the right hand the right hand side equality of this thing in the square rectangle. Del
That is a,
of Q.
that is definition. That is definition. You know what a Dirac delta function is, right?
I mean, yes, we studied it, but I can't recall if it was the ratio of these two
That is not how
delts.
it is defined. That's not the definition of Dirac delta function.
The
This, I'm sorry, this is not a definition of Dirac delta function. This is a formula which is giving a functional derivative of something.
Okay.
Quick question: how many of you have never heard of Dirac delta function? One. Okay, so most people know. So maybe, okay, two. Fine. Any more? Okay, so I'll give a reference and you can read it up. Okay. So. So, reference on the Dirac delta function is it's an article all about the Dirac delta function by V. Balakrishnan. It appears in Resonance. I'll even put it up maybe on. Okay, it's an article in this beautiful journal called Resonance. Okay, so this is something which you can refer to. So, but from our viewpoint, property, just the key property. Okay, so you let's say you have some function of time. Okay, and then any arbitrary function of time. And then, okay, and for simplicity, we will just say it's a function from 0 to t, but it could, you can change the limits, you can do anything you want. Okay, so this is the property. Okay. So this is the key property, is that it picks out the value of this function at this time t. That's what it does. And if you try to, so the point here is that if you try to understand what this thing is, so you can see that in this integral, that from this you can guess properties. Delta of t minus t naught is 0 when t is not equal to t. Okay, but when it's equal to t naught, it's actually not, it can't be 1 because there is this integration, so it's like 1 by dt or something, 1 by epsilon. So it's and delta of 0 is actually infinity, such that the area is 1. Okay, so if you take the case of so its value is infinity, such that integral 0 to 1 t dt delta of t minus t naught equal to 1. Okay, you just take f of t to be 1. So these are properties of the Dirac delta function. Okay. So this is the only property that I need. Okay. So you can go ahead and read this. I'm sorry. So as far as I can see, this does not, I hope it is clear to you people that this thing does not define, this particular equation does not define Dirac delta function. It's like it's like saying taking derivative of x squared equal to 2x defines 2x. I mean, come on, that's not correct, no? So this is just a functional derivative. So this is what it says. Okay. So, and it's also, if you know something, it's a delta function, it's a direct delta function is not a function, but it's something more general than that. It's a distribution, whatever. But that's, we don't need all that, because what we will do is always put it inside an integral and where it makes sense. Okay. So I'll pause here. Does this make sense now? This formula? It's just matching these two things. So here you can see that that's what I'm doing, right? I'm using that property. I took f of x to be delta q of t. That's what I've done. Is that clear? So it's like an indicator function. It picks the value where it becomes 0. That's all. But it only makes sense when it is within an integral. Okay. But formally we can write stuff like this. But this actually will make sense only inside some integral. Okay. At the end of the day. Okay. So let's do second example. Okay. This is equal to now this in the function picks out the value of the derivative at t naught. Okay, so again this is a functional, and we want to work out what is the functional derivative. Interrupt me if something is not clear. That's what we get. And this cancels. Just like before. So we get delta q prime of t naught, but I want to write this with an integral, and now comes the interesting, the correct way, the way to do this. This is equal to integral 0 to t dt. Again, I will use the indicator function. I mean, with that delta function, it picks. Now I'll take f of q to be f of x, f of t to be delta q prime, that is. Okay, this prime means it's just delta q is some function. You take its derivative with respect to time, it's at same time equal to 0. Okay, so let me just do this slightly differently here.
So it will be delta q prime of t, right? Okay, so I mean, you have written it t naught inside the bracket. Should it be delta?
Okay, but now we have a problem. We have a problem. What is the problem? The problem is that let's come back here. So we want to write it as an integral with delta q of t. This is what we want, but that's not what we have. So what we will do is integrate by parts. Okay, so now integrate by parts. There'll be a minus sign. Plus total derivative, which vanishes. Okay, why do they go to 0? Because let's come back. We have said t naught is does not include, so t naught belongs to 0 into the open interval with 0 and t, so it does not take values 0 and t. Okay. So delta of t naught will always vanish. Delta of t minus t naught will vanish at 0 and capital T. Okay, so these terms will drop out. So this is not there. So this is what we get. Now again, we can compare with before, and so let's put a box, red color. Yeah. And this should be equal to delta dt0 of q divided by delta Q. Okay, and it's an exercise which I'll leave it for you. You can now, this is a delta function as a function of two variables t and t naught. So I could even write it like this. Okay, so this you can check for yourself. So this is what we get. So what we get, so now again we can do the same thing, dt of t.
Hello.
Yes.
Sir, this delta d t0 q over delta qt, is this a functional derivative calculated at t0?
No, it's not. No, it's not calculated at t0. It's just a functional derivative of this function. No, t0 is a parameter in the
Okay, sir. It's used to define the functional. Okay,
it
sir.
It's some it's there. It's a constant in the function.
Okay, sir.
Okay, so this is just some parenthetical remark. I mean, this is the key answer. So what we can, so we again, I'll plug in what? Delta Q prime of T naught Okay, so now I can exercise which you can generalize this several times over. So the nth derivative with respect to time evaluated at t naught very easy to, you just keep using this recursively, you get this. Okay, so I'm defining a new functional whose value is the nth derivative of this function q of t. So these are two examples that I have. So again, I'll pause. Are there any questions? Comments? Okay. Third example is the following functional. Let me put a minus sign just for, I don't need to put a minus sign. Okay. So what is happening here is this functional is there is some, you're given some function v of q, it's only a function of q, and we would like to compute what the functional derivative of this would be. Okay, so we did special cases last time. We did when v of q was some q power p we had done. Okay, so it's the same thing. Okay, so if you just go ahead and do this. Okay, so now what we will do is the time dependence of this term is buried inside this q. So we'll act. So what we can do is we can just, this is some function of a variable q, of some single variable. So we can just write this as follows. This can be written as dv by dq. It's just normal derivative with respect to this. Okay. After this cancels times delta q. This is just Taylor series of function. Okay, so So now we can just go ahead and compare. And so the coefficient of delta Q of T is our this thing. So what we get is delta F1 of Q there is this minus sign here, so I should keep on carrying that minus okay, so notice that there are two different deltas appearing here. One is this is the functional derivative, and this is the partial derivative. Okay, so this is functional derivative, this is partial derivative. Okay, actually it can be even ordinary derivative. I could have used d also here because it's a function of one variable, but okay. So this is what we get. Is this computation clear? Anybody? So you can see that if you put v,
Yes,
last time's thing, if you put q power p or something, we get pq p power minus 1. Last time's result just comes through. This minus sign is because I put a minus sign in this definition. There is some weird reason for it, but okay, it's not so. It's not relevant for this computation. Example 4. We are building up to something, okay? So, and you can see I'm increasing the complexity also. Now, t is some function which is only a function of q dot. It's not a function of q. Okay, so we want to work out what this is. So let's do this again. Again, it is nothing. You have to just sit with the formula and do it. Okay, again we can do Taylor series because t is just some function of one variable, and so I can write something like this: 0 to t dt partial derivative with respect to dq dot, which is its function, times delta q dot, which I'll write as d by dt of delta q dot. Okay, but we want it in terms of delta q, so what should I do? What should I do next?
Integration by parts.
Integrate by parts, and the surface term will vanish because delta q of 0, so we have to use delta q of 0 equal to 0, delta q of t is 0, okay, because the endpoints are not changing. So we do this, integrate by parts, you get a minus sign, so we get integral 0 to t dt minus d by dt of okay, so now we are ready to identify the functional derivative, whatever comes between the integral and delta q, that's all we need. This is what we get. Okay, is this clear? So next example is kind of very, what is this? Example 4, is it? Let's do example 5. Okay, example 5 is the following. The functional is consider f of q to be f1 of q plus f2 of q. The ones we just defined. Okay, so now the important point is property of functional derivatives is that if you take linear combinations or you scale them, functional derivatives will go through. So you can check for yourself that delta f Okay, so you can check this formula. Very easy. Okay, there's another thing which you can also check for another property. Which is the important property, which says that if let G1 and G2 be two functionals, then you consider G to be the functional which is G1 times G2. It's not hard to see that G is also a functional if G1 and G2 are. Okay, so can someone guess what the answer should be? Anybody? Okay, let's ask a slightly different question. Let's say that G1 and G2 are two functions, and I construct a function G and of time, say, G1 times G2. So what can you tell me about the dg by dt?
It will be a G1 into G2 by dt plus yes.
This has a name, no? What is this rule called? Leibniz rule. Chain rule or whatever. Okay, so Leibniz, I'm getting his spelling right. Okay, so same thing goes through. So this is the most important property of derivative. Something you want to call a derivative, okay? It better satisfies this rule. Okay, and the first rule is kind of obvious, but very easy to check. Go back to the definition and check.
Hello.
Yeah.
Sir, is there a specific reason why we are not using the usual D sign, but using this del sign?
Yeah, because it's not G is a functional and this is a function. So here when you did, right, if you give me, this is a number. Okay, output here, this is a function. G is a number. Once you feed it some q, but once you take its functional derivative, you get a new function, right? I mean, these are all functions, right? I mean, whatever this is, right? Some function. D by dt, you do all those things, you evaluate it, you will get something.
But sir, I think dg by dt in the right hand side, small g, dg by dt is also a function, right? It is also a function.
Yeah. Okay. No. The point here is that you fix a value of t and you compute it, you get. I mean, so this is no, but G. The point. What I'm saying is, this is a function. This is a functional. Okay. I hope you understand the difference.
For a particular value of t, dg dt will give a number, and for a particular value of q, d dt will give a function.
Yeah. That's what I mean.
Okay.
So the analog of fixing q here is fixing time on the right hand side. Okay. Good point actually. Okay.
Okay, sir.
So if we took a derivative of capital G with respect to time and fix the time at a particular point, then it would give a number, no?
It is zero. It is zero.
No,
No, because
I mean that after taking the derivative, then we fix the time.
Yeah, then it will give a number.
Yeah.
It is just a value of a function.
Chain rule. So it's like function of a function, right? So then you will do something like this. What you are saying is something like this, right? So yeah, but that's yeah. So
It will just be the value of a function at a point. So if we fix the time.
yeah. So I mean, the thing is that there is no time on G. This is what I'm trying to say. It takes input a function. Function is Q. I mean, that's all. T is some parameter implicit inside Q. So by itself, I wouldn't. I mean, this makes sense. I won't. I mean, I will not. What I'm trying to say here is, suppose I have. Let's think of some function f, which is some integral 0 to t dt f of t. Okay. So now my question, so now here is right and left hand side has no time. Here you have integrated all the time. So they just, I mean, this thing. So I don't know what, there is no time. So df by dt doesn't make sense. Because this is, like we saw, this, the correct statement here is, this is f of f. That's all.
Okay, sir. Understood.
Hello?
Yeah.
Sir, does d of capital F divided by d of small f makes any sense?
Yeah, that is what this is. That's what the whole function derivative is.
That is what I was asking, that why aren't we using the usual d sign rather
No,
than...
we don't. We
Yeah.
don't, because what comes out of that thing is a different object.
Okay.
I mean, if you feel, I mean, this is convention. And I think there's a good reason. There's a good reason for. There's a good reason for doing that. Okay?
Okay, sir.
Okay, so let's just finish. We have done this thing, right? So we have to do, now coming back to our computation, delta F by delta Q. So the first one gave us minus dV by dQ, right? And the other one gave us minus okay, so this came from F1 and this came from F2. Okay, just using this property. I'm just using this property. Okay, so this is the answer. Now I will example 6. Okay. And we'll give this a name. We'll call this the action functional. And L is some function of two variables now. Okay, it depends on Q and Q dot. Okay, so exercise. This is probably the most important exercise ever. Show that Okay, so key point here is on the this is something which you should think about a little bit. On the left hand side, we are only giving q of t, but what we are giving is the full q of t. So q and q dot are, I mean, if you give me q of t, you know, q dot can be computed, right? Taking a derivative, right? If you give me the full function, I can always find out the slope at every point, because you need two numbers, right? But let's come to the right hand side and let's look at this function. Now this is a function of two variables, but in the integrand, it's at a particular time. dt you're integrating, so it is actually a fixed time. So here on the right hand side, q and q dot are independent. You understand? Because it's at a given time. If you fix a time, you pick some time between 0 and t. So 0 and t, you pick some time t. So at that time, q and q dot are independent. Is this point clear? The value of a function at a given time and its derivative are independent at the same time. Because if you know the value of a function at a given point, you know nothing more about the function. If you want to know the first derivative, you need to know something, you need to know one more number, no neighborhood point. Is that clear? That you need two numbers to evaluate a derivative.
Yes, sir.
Huh?
Yes, sir. Yes.
Okay. So here also, in that sense, so on the right hand side of this, q and q dot are independent variables. So you're doing, so now partial derivative makes sense. Partial derivative with respect to the first variable, and this is the partial derivative with respect to the second variable. Okay, so you write this out. You do this. Okay, so prove this, and I will do the last exercise. Not exercise, example. Okay, so let S of Q be the following function be equal to okay. So this is pretty much like our F example, right? F1 plus F2. So this is like F1 and this is like F2, and we can so now we have to do, we can work out what delta S by delta Q is. Okay, and so I'll just do it. It becomes minus d by dt, so minus q double dot, and this fellow will become minus dv by dq. Okay, so this is just combining the results from this is example 7, right? So 4 and 5. This is what we get, and extremize doing this. Implies what? Set the functional derivative to 0. If we do that thing, we get m Have you seen this equation somewhere?
Newton's second law.
Yeah, Newton's equations of motion. Okay, so what is the consequence? So, in other words,
Sir, the existence of potential itself means the forces are conservative. So
yeah.
okay.
This is something we couldn't have guessed, So it's like the Pachistochrone problem, what we got as Newton's laws. Okay. So, one more thing, it's important here to realize that what we are getting are functions. When we do the functional derivatives, so we're getting, and their derivatives, so we're getting a differential equation. So extremizing functionals will give you differential equations. Okay. So this is something which is remarkable. Do you agree? One would not have thought that this would be the case, maybe it can't be or whatever, So this is something which is truly remarkable. And so what happens is in classical mechanics, we use the following generalization. Okay. They say that let's write a different color. The equations of motion are given by the extremum of the action function. Okay, so this has a name. This is sometimes called principle of least action. Okay, so one caution is, can we write a functional when we don't have conservative forces? And the answer is no. Okay, so obviously there exists. So we'll make this remark. Equations, okay, arise this way. Okay, so this is important. But then, okay, so if this is the case, however, it turns out that a large class dynamical systems arise in this fashion. Okay, so that is this picture. How much time do I have? I'm almost done. Okay, so we have this, let's say this box is a general dynamical system. Okay, so one small, this would be, sets, dynamical systems which arise from action. Okay, so the general dynamical systems are very, very interesting. They don't have to arise from actions, but for some weird reason, which is not entirely obvious, that a large class of systems can be large class of physically relevant and useful systems fit into the framework of the equations of motion are given by the extremum of the actional function. So the next few lectures, we will be spending our time. We'll come back to looking at more general dynamical systems later, but we'll focus on understanding this idea. So the great thing about this principle is that it comes down to asking what is the action functional. Can we write so we want to model some system, and let's assume that we are able to model it with some action functional. So it comes down to just figuring out what the relevant action functional is. And we'll find that there are lots of things which inputs can be put in, and you can put conditions. And sometimes that, in fact, lets you completely determine the action functional. I mean, sometimes you get very lucky. Okay. So I think I'll stop here and pause for questions. And yeah, go ahead.
The small set of generalized dynamical systems that comes out of actions are the ones that are actually physically possible, right?
No, that is wrong. No, I'll give you one simple example. A damped harmonic oscillator, that's physically possible, right?
Okay, so that won't come out of action.
Dissipation, for instance, we can't, I mean, our whole class just take these equations and add dissipation to it. Bingo, it's out of this. Okay?
We can't take any potential for that.
Yeah. Okay. So, but, I mean, but these are very, very important subclass. I mean, this is the key. I mean, the whole point is that if you go back and you ask at a fundamental level, how do, particles interact, etc. It turns out that they are all in this category. All the fundamental forces come into this category. Maxwell's equations comes into this. Okay, so it's pretty remarkable. Okay. But, I mean, we also understand, dissipation in a different way, etc. But that does require sophistication and things like that. But there is no guarantee that, it's wrong statement to say that these are the only examples of interest. It's just that it gives you a large class of interesting examples. And we don't understand why this island or whatever, this small thing is very, very, important or whatever. We just know that. Okay. So any other questions?
Yes, sir. So saying that systems are arising from action is the same that they are being acted upon by conservative forces only?
No, that's not the only. Yeah, there's more structure to it than this. That is too trivial statement.
So are we going to learn that in further classes? Or
Yeah, we will see.
Okay.
We will see. Yeah.
Okay.
Definitely.
So can there be a better framework to include the dissipation cases as well, similar to this action functional?
So there are, yes and no. I mean, yes, in the sense that there is, so usually one way of saying that is that when you have dissipation, you have energy loss. That means there are some degrees of freedom which you are not putting into the system. Okay, so energy can go into those things. So you could combine those things and get a larger action so in quantum mechanical system, there's a path integral way. It says you integrate out some degrees of freedom, whatever that means. And then you get the effect of that will look like a dissipation. So those kind of things happen. So there is some class of dissipations which we can include in this fashion. I wouldn't swear that that's the only kind of dissipation, but yes. But usually that's what happens at a fundamental level. Okay, so. Okay, let me stop recording.